Plus, you just editing papers. Anybody else? Are you editing?
I think so. Let me straight.
Something not around. What was wrong?
I don't think so. I'm not very sure.
Okay. Okay, let's get started. Welcome to the last lecture in the last part of the spectral component of this lecture series. So this lecture will have two parts. The first part, which will be about half an hour, will be completion of the zigzag expander construction. With that, the spectral graph theory will be completed and we'll start a completely new topic. This will be just for the toolkit course, not for the high dimensional expanders sequence of lectures. So what we were doing last time, we were discussing this construction of expanders. So via the zigzag product. So recall from last time, we had defined this notion of a zigzag product. So if I give you a graph G, which is an N D lambda spectral expander, that's a graph on N vertices, it's capital D regular, and the max of the second eigenvalue and the absolute value of the lowest eigenvalue is at most lambda. Think of G as a large graph on capital N vertices. H is a small graph. It's only on capital D vertices. D, its degree is small lambda, and its eigenvalue is this. It's a spectral expander of these. Using these, we were going to construct something called the zigzag product of GZH. And we'll go over the product. This was going to be a graph on n times d, n times capital D number of vertices. Its degree will be small d square. And its spectral value will be at most this quantity. We are yet to prove this. We are yet to prove the part on spectral expander. We were in the midst of proving it in the last lecture. So, but let's remind ourselves what the zigzag product. Yes. So G is a graph on n vertices, which is capital D regular. H is a graph on small d, so capital D vertices, which is small d regular. So the very first step, what you're going to do, how are we going to construct the zigzag product? We take the graph G, we blow up each vertex into a cloud. So each vertex in the big graph becomes a cloud, and in the cloud, we are going to stamp a copy of the graph H. So every vertex of the original graph, there is a cloud now. And this cloud is connected to another cloud. This one. So vertices have not yet been connected. One cloud is connected to another cloud. Those are the edges of G. And within each cloud, we have a full copy of H. That's the ND vertices. The vertices are you have to tell me the address of the cloud and the address of the vertex within the cloud. So it's capital ND vertices. So the vertex set, the vertices of this one is exactly vertices of G cross vertices of H, which is the same, which is N cross D. And so a single vertex is sort of blown into a cloud. So think of two clouds sitting there. And there's a full copy of H. Sitting here. So let's think of a vertex here is a typical vertex here is of the label U comma A. Let's say the name of vertex U. So U belongs to capital N, A belongs to capital D. And we're going to explain what, and let I and J both belong to D. We are going to explain what the ijth neighbor of UV is. This is what we are going to describe. How do we do it? We first take the ith neighbor of A within the cloud, within the current cloud. So we go from, so this is I, and that takes you to say UA prime. So firstly, what is that? So A prime, so if you apply the rotation map H on A comma I, we get A prime comma I prime. Okay, so that's within this map. Then we are at UA prime. We take the step corresponding, we take the A prime neighbor of U in the graph G. So that's the next step. The next step is rot H, rot G of U A prime. Let that be V B prime. So we take that giant step. We go to V B prime. Notice that this step did not involve any of the which address to go to. Once you've done the first step, this is a deterministic step. What I mean is you don't need the address of you don't need to know which edge you are. Once you're in UA prime, there's only a unique thing you can go to, which is VB prime. You don't need to look at I and J to do this. Then you take the step. Then you take the jth neighbor of B prime within that cloud. That possibly takes you to VB. You then apply rot H of B prime on J, and we get B comma J prime. So the output is going to be, so the output vertex is B comma B. That's the edge. And this edge is labeled by I comma J. Because if you take the ij step, that's how you walk. And notice, if you take the J prime step and then the I prime step, you will retrace back. So this is actually I prime. This is J prime. Therefore, this direction would be J prime, I prime. So in particular, so if you run these three things, then rotten GZH of U comma A, I comma J is equal to V comma B, J prime comma I prime. Is that okay? This is the zigzag product we define. So there's a first step in which you mix in this cloud. You take a random step in the cloud, sort of you mix in the cloud. So if things are not uniform on the cloud, you mix on the cloud. And then you take that's a local small step. It's an intra-cloud step. Then you take a giant step. Now you are mixing across clouds. And then you again mix back within a cloud. So it's 3 steps. And it looks like a Z. That's why it's called the zigzag product.
So B prime.
Yeah.
How do we know the B prime? I mean, how is it?
So it is the A prime neighbor of U is B. And it is the.
There's a nice, I mean, since the capital D, the capital D, which is the degree of the G, is also the identity of the vertices in the small graph.
Yeah.
So when you're doing rod H, there the A is saying which vertex in the small graph you're taking, but in rod G, that A prime is saying which neighbor you are.
Yeah. So this here A is playing 2 roles here. Here it is A is B, because this is important out here. These 2 guys are matching. And that's important for the tensor product to happen, the zigzag product to happen. The degree of the large vertex should be equal to the number of vertices. So as Varun said, in this first step, I'm using A as the I'm using A's identity to find out which vertex it is in the cloud. So it is the eighth vertex in the cloud. And it has moved to some other A prime, this one. So now you are at the A prime vertex in this particular cloud. But now you change its identity, view A prime as it telling you which neighbor of U you have to go to. And it tells you the A prime neighbor of U is V. And from V's point of view, U is the B prime neighbor. That's the rot. This is the thing which you said, hum aapke hai kaun. So the rot map tells you the usual neighborhood. This is the A prime neighbor of U is V. But it furthermore tells you from V's point of view, the B prime neighbor of V is actually U. So B prime is that. And it's important to know. Notice for writing the zigzag product, I need to know the rotation map. Okay, so is now B prime clear? And then you know B prime. From B prime, you then take the step. Now you come back to B prime was now here interpreted as the degree of the large graph. Now it becomes again interpreted as a vertex in the small graph. And then you take a step. So let's take a simple case which will actually be quite important in the proof. Let's ask what happens when H is actually KD star. It's the complete graph, sorry, K capital D star, which is a complete graph but with self loops. So this is it's a graph on D vertices. Its degree is also D because it's connected to every other vertex, and second eigenvalue is 0 because the complete graph is only all ones and then it's 0. Let's see what happens. So how does a zigzag step look like? So you start with a vertex. What will the first step do? It essentially takes you to a random step within the cloud. It takes you a random thing within the cloud. And then you take a step out, which is now taking just that essentially means you are at some UA, you forget this identity of A, and you just move to a random neighbor of U. And once you go there, you once again pick a random one of the elements D, and that's it. That's what it does. So that's what it does in terms of a walk. But let's ask what it does in terms of function. So suppose you had a function, we would be interested, we would be eventually, because we want to understand the eigenvalues of we want to understand the spectral gap, we would be interested in how the random walk modifies functions on it. If say W is we define W to be the random walk corresponding to GZH. I would like to understand and F is and F belongs to say R cross NT. And furthermore, let F be orthogonal to the all ones function. We know the all ones function is always the first eigenvector. We would like to understand how W behaves on F to understand how much it shrinks. This will tell you the spectral gap. Let's ask this for the simple, to understand. So what I want to say is to understand spectral gap. This. To understand lambda of GZH, it suffices to find how does
Prahlad, I missed last time. So, what is the number of edges between the clouds? Is there one?
No.
Yeah. Could you just say that one?
Yeah. So let's look at it. So, so the bit. So
is
original.
it a random graph construction or is it a?
Sorry, can you repeat your question again? Actually,
go ahead, sir.
So let me state it and
so
say.
Is it a
There is the original graph G,
okay,
which is a capital D regular graph. There's the graph G, which is on n vertices.
Yeah.
And it had, and
yeah.
it is.
So let's say it's an expander. It's a deregular expander. Fine.
Yeah. Now you just.
And then you blow up the vertices. What is the edges between? Say, yeah.
And there are the original edges between the clouds. You're now just.
I see. So
the vertex.
I see.
A cloud. And now in the place.
But these edges. The edges go between which vertices? So that's what I'm asking. So you have a choice.
The vertices of the new graph are this. So the edges, the vertices.
Yeah. So
cloud address.
So is it a complete bipartite?
It's not
a complete bipartite.
Not the complete. So let's go over it again. So what are the edges? The edge structure is going to go this way. This is going to be a d-square regular graph. Small d. So it's not a complete graph. It's far from a complete graph. And it's a small d-square regular graph. So I will tell you what is the ijth neighbor for every I and j in D.
I see. Okay, fine.
And then this is the procedure by which I'm doing it. So I first take a step within the cloud specified by I. Then I take a step across the cloud specified by which vertex I am in the current cloud. And then I take a step in the second cloud based on j.
Yeah, and so the thing is, this is because it depends on a random walk on the small graph. It's a random graph construction. Is that right?
If the small graph is a fixed construction, it's a fixed construction.
Okay.
If G and H are fixed, this is a fixed construction. This is a deterministic construction.
Okay, fine.
Yeah.
But okay, in that case, your ROT is some map that you define ahead of time.
So ROT, okay. What is ROT? This was something I defined. Usually we define, so let's just recall what ROT is. Usually when you have a graph, when you have a graph is an ND regular graph, we have the neighborhood function which takes n cross D to n, which tells me who is my, basically this maps n comma I, it maps v comma a to the eighth neighbor of v. That's the usual neighborhood map.
I see.
But ROT is a slightly.
I was thinking that. Okay. No, I thought you were picking A at random. That's what.
No. But ROT is a slightly more sophisticated. It's a slightly finer version of the above function. It's not so you give v comma a. You not only give the eighth neighbor. So suppose there's v comma a. There's v, and it has, say, this is the eighth neighbor of this one. You go to u. And it asks, from u's point of view, what is, if for u, v is the bth neighbor, then your output b.
Nice. Okay, great. Thanks.
So this is, so ROT G is an involution.
Yeah. Okay,
involution on n cross D.
Okay, thanks. Sorry for interrupting. Okay, go ahead. Yeah.
Okay. So this one. So we want to understand. I'm going to move this. That's this part. So we want to understand the spectral gap of this product. So what does it mean to understand a spectral gap of this product? So you want to understand how does the random walk on G ZH behave on, take any vectors in the corresponding space, which is ND. You know this is a regular graph, therefore it will on the all ones vector, it's going to just take it to the all ones vector. So we'll behave on F, where F is orthogonal to the all ones vector. You want to ask how does it behave? How much does, you're rather asking, how small is this W F compare versus F, where W is the random walk matrix on GZH. Is that fine? Let's just get our hands dirty. This is what we said last time. Let's look at the special case when H is KD star. That is the complete graph with self loops. And this particular case, so let's take this special case for now to begin with. And let's ask, in this case, what is WF compared to F for F, which is, this is what we want to ask. Now, what does WF do? WF is a random walk matrix. It basically looks at the distribution of things you go. It averages F based on the random walk. It's going to take the average of all its neighbors, how the random walk is going to average it out. Now, let's look at what exactly it's going to do for this particular function. The first step is a random walk in the cloud, and it's a complete random walk. So it's when it takes averages, the first average is just going to replace everything in the cloud by the average of the elements in that cloud. Because I'm working with a special case KD star, the first step is just going to replace every vertex within the cloud by the average value in the cloud. So let's write. So given F, what I'm going to do is I'm going to write F as F parallel plus F perp, where F parallel is constant within each cloud. Okay. And furthermore, so I'm taking the average, writing the constant. So that is F parallel. F parallel is basically this, what I get by average. So F parallel is an F perp, where F perp and F perp has the property that within each cloud, within each cloud of each vertex V, this one is orthogonal to the all ones within that cloud of V, for all V in capital N. So it's basically within each cloud, it is splitting it as the all ones vector in that place plus its orthogonal component just within the cloud. This is, and for it's doing it separately for each vertex, each single cloud. And we are accumulating all of that. We are taking all of that, putting in F parallel, F perp is all the rest. And notice that the first step basically is taking F to F parallel. It completely destroys F perp from the picture. The first step takes F to F parallel. The next, so now once it's F parallel, it's essentially the step is now like a G walk. You basically are going to take a step according to G. It's distributing it equally likely among all its neighbors and taking a G step. And now the next step is averaging it over there. So what I claim is it should not be hard to see. Now, firstly, there are two things. The first observation I want to make is it should be clear that F perp, F parallel is certainly less than or equal to F, because this is just an averaging operator. Its norm only reduces. That's observation 1. Observation 2, I want to say, is WF is the same as WF parallel. These two, it doesn't distinguish. The very first step throws out F perp completely. And this is just G of F restricted to the clouds, F restricted to G, tensored with the all one, tensored with. It's essentially when you take this F per, there is actually no G good. There is H loses its significance completely because you're taking a cloud, you're taking a last step and you're averaging again. So it's essentially as if you replace every F by what the values are on that particular cloud. You take a step on G, you take a step according to G, and then once again you spread it uniformly across all the vertices. You average it out again then. So I claim this should be clear from this. That is, let's write this. This is, I want to write this is exactly G times, or rather WG times this vector, which I'm going to call G, tensored with the all ones vector on the cloud H. And what is G? G is just G is a function where G is a function on the vertices of the large thing to R, such that G of every V is exactly F parallel V for A, for any A. You know, it's a constant function. So I could have chosen any A. It is that guy. It's just that value I'm putting it there. So notice that this step should exactly be this step. It is just, it's averaging it out. It's basically taking a walk according to G. And notice this G, and G is also perpendicular to the all ones function with respect to the graph G. Because F was perpendicular to all ones. This is just local averages, so it's still the sum will be orthogonal to this. So all I claim out here is WG. Sorry, this is not, this is G. WG of G is certainly less than or equal to lambda of G. This is just follows from the G spectral expansion. Therefore, all I'm claiming is WF length is at most WG's length. This is that one will, the length of one is one, so it's just that, which is exactly, which is at most length of lambda of G, but this is lambda of F parallel, which is less than lambda of F. All the sequence of inequalities here, Clive. WF is in fact, this is, there is no inequality here. This is an equality. This is the way things are constructed. This one is because of the spectral expansion of the large graph. But G, the size of G, the norm of G is the same as norm of, that's not F derivative, that's F parallel. F parallel. But the F parallel is utmost size of F. So what have we got? We have the conclusion from this, the claim from this is the spectral gap of G tensored with KD star is less than or equal to just lambda of G. So far, so good. That if we had not taken H to be a, notice this process is, this is not a process we want to. We wanted to reduce the degree. We are not going to zigzag it with the complete graph. We want to zigzag it with a small d regular graph. But had I zigzagged it with the capital D regular graph, then I get back, then I've done nothing. I've basically taken one random step locally, taken the step according to G. So I've done nothing. So it's still the eigenvalue spectral gap of the original graph. But now let's come to the general case is when H is a DD mu spectral expander. In this case, what did we notice? We noticed a while ago, in fact, 2 lectures ago, that the random walk on H can be decomposed as 1 minus mu times the random walk on KD star plus mu times an error vector where the norm of WE is always less than or equal to. We can always decompose it this. This was something we did last time. So W, the random walk GZH. What was this random walk? We noticed what this random walk was. This random walk was, the first step was, it didn't change the I component, I on G, but it's a random walk on H. Then you did rot G, the matrix rot G with the permutation matrix. And then once again, you did. This is shorthand for the entire random walk on GCH. This we had recalled. This just followed from the definition of. Okay. So this we can write it now as IG tensor 1 minus mu WKD star plus WE dot rot G. We did all of this last time. IG tensor 1 minus mu. We need to put this in parentheses. Okay. Let's collect. So far, so good. So let's collect. There's a 1 minus mu whole square IG tensor WKD star rot G IG tensor WKD star. Plus, how do the other terms look like? There's 1 mu into 1 minus mu IG tensor WE rot G IG tensor WKD star plus another mu into 1 minus mu IG tensor WKD star rot G IG tensor WE plus mu square into IG tensor WE rot G IG tensor WE. I just collected the 4 different terms that you get in this. Yeah.
I just wanted to see the previous. So, okay.
So we can always write any graph with a spectral gap whose second eigenvalue is at most mu.
No, that's okay. For some reason, I thought that was a inequality instead of equality.
No, you can always write it as that. You can push everything into WE. You can always write it as this one. We don't know what WE is. WE is some vector, some matrix with norm is at most 1. This was actually a perfect equality. If you recall, we did this 2 lectures ago. It was that way. We had this, we had this matrix W end. Therefore, we could write it down as Wn plus We. So we could exactly write W as 1 minus lambda plus We, where We was less than lambda. So I just pulled out lambda and I'm calling it this. So we did have this exact. Okay. I want to look at the norm of this whole matrix. Now, norms behave very nicely with both tensor product and product. The product of 2 matrices, the norm of the product is the product of the norms. The norm of the tensor product is also the product of the norms. Works nicely. So this one, WE has 1. Everything else doesn't alter it by 1. So this has at most norm 1. This has at most norm 1 without the scaling factors. norm 1, norm 1, and then you add up all of these. So at the end of this, I want to claim all that you have is 1 minus mu square Ig tensor WKD star rot G Ig tensor WKD star. This is a graph which we already knew how to analyze. This particular graph, this was a special case which we did. Plus, I'm collecting mu, 1 minus mu, all of those. That's just 1 minus mu square into some VE, where the norm of VE is at most 1. You just collect all of them. The norm of the whole thing will just be at most. The norm of the sum of these three things will exactly be the sum of these three. So it's at most this. Keep it with me so far. Varun, you don't seem happy.
So eventually you want to just say that when you apply this whole thing on F, then that is going to be at most whatever the final boundary was.
So basically we have almost gotten what we want to do. See, we almost got to now let F be any vector in R and D, and F is parallel to the all ones. This all ones on the ND in the ND space. So in GZH. Let's decompose F as F is equal to F parallel plus F perp, where once again F parallel is just you replace is constant on each cloud. You replace each cloud by the constant vector on that cloud. You average it on the cloud and replace it. And F perp is such that it's going from the average to the back to the original F. It's the difference vector. So F perp with respect to every cloud of V is actually it will be orthogonal to the all ones vector on the cloud of V for all V in N. It's the old decomposition which we did. So now let's understand how does WGZH behave on this F. By what we have here, this is just 1 minus mu square WGZ KD star on F plus 1 minus mu square VE on F. When we are done, WGZ H of F. The first one, this one, we know it's shrunk it by at most lambda. Therefore, this is at most lambda into 1 minus mu square of size of F. This is a norm, V has norm 1. Therefore, that's at most F. And what is this? This, if you look at it, this is 1 minus lambda, 1 minus mu square of size of. So hence lambda of WGZH is at most 1 minus lambda, 1 minus mu square. So let's remember. So the key thing about the exact product is this.
The gap of G.
So let's go back to the old things we wanted to ask. How does the number of vertices behave? How does the degree behave? And how does lambda behave? The number, so the degree is what actually improves dramatically. The degree was capital D, it's reduced to small d square. So this went from D to D square, and that's a very good feature. That's what we want. The number of vertices went from N to ND. It's not as bad as tensoring. It is like tensoring. This is not bad, it's reasonable. Lambda deteriorates. This is certainly worse than lambda. This is certainly smaller than lambda. Because if mu is 0, this is lambda. And larger mu takes, this is going to go worse than lambda. Similarly, it's smaller than mu was. It's actually smaller than mu. So it's worse than both. But it says if you have constant lambda and constant mu, this is also a constant. So this one is actually deterioration. It goes from lambda mu to 1 minus lambda 1 minus mu square. So this is a deterioration. But notice the other operation which we had squares and all, they all improved lambda or they improved the number of vertices, but always deteriorated degree. This is an operation which improves the degree and possibly affects the other one. So now you have a set of operations. You have squaring, tensoring, and zigzag, each of which improves one parameter and possibly affects the other two parameters. The question is, can we put them together to actually get a family of graphs? So let us see that.
So this vertex is increasing, that's a good thing, right? Because we want the
vertex is increasing is a, yeah. So in this one, you can change that to a happy face if you want to, yeah. The most important thing of here is D is going to D square. So let's exactly construct an explicit expander family. Our starting point is going to be a graph H, which is a D. In fact, no, it is around B. A D power 4, D 1/8 spectral expander. For some fixed constant D. So fix a particular D, say D be 10 or 8 or something, for such that 1/8 is allowed by the Allor-Bopanna bound. That is, it's not smaller than the Ramanujan one. So choose a D large enough so that you can get this. And now you can do a brute, it's a constant size graph. Do a brute force search, lay your hands on such a graph. You know there exists an expander, a random capital D regular graph on D power 4 vertices will be an expander. Just run over all of them, pick the best guy. And from this, we are going to construct. So this is going to be construction 1. We are going to construct a family of graphs where G1 is H square and GT plus 1 is just GT square zigzagged with H. Let us see why we can do it. And the claim is going to be GT is a T power 4T D square half spectral expander. This, firstly, we need to see if we can actually do zigzag. To do zigzag, the degree of GT should be equal to the number of vertices of H. The degree of GT we are always claiming is D square. In the first case also it is D square because you're still squaring it. So it's always D square, and of GT is D square. So GT square is D power 4, which is exactly the number of vertices in H. So zigzag product is well defined. You can do the zigzag product. So the zigzag product will be a thing on how many vertices? It will be the product of these two guys. So it's now D power 4t minus 1 into another D power 4. That is exactly D power 4t. Its thing will be the square of the degree of H. H was a D regular, so it's D square regular. And you have to check this. Check this is just check by induction that those two will have this property. So you are constructing. Now we just started off with one graph of that type, and then doing just zigzag and squaring alternatively is constructing a whole family of such graphs for every t. Is that okay? So this is an fully explicit construction. Not, it's an explicit construction. Let's ask if it's fully explicit. How much time do we take to do this construction? What's the time taken to construct the teeth graph in this process? So let's ask about explicitness. Let's say time t is the time taken to construct the teeth graph in it. I want basically I'm asking if I give you a vertex and its neighbor number, how much time does it take me to compute the next thing?
So we're going to instantiate for t being like log. Like if we want n sized
graph t is going to be log n, yes. So okay. So let's ask how does time t depend on t? Notice to do time t recursively so let's actually do time t plus 1, which is, so let's define time t is the amount of time required to compute ith neighbor of a vertex in GT. Basically the rot map. How much time does it take to compute the rot map? So I claim time t plus 1 is 2 times time t because I have to square the graph. So I have to take 2 steps. Plus an order 1 operation. What's the solution to such a recurrence? The solution to such a recurrence is time t is 2 power order t. This is too bad for us. So if you want for the teeth graph, the amount of time taken should be poly t if it's fully explicit. This is only weakly explicit. So this construction, so it's a weakly explicit construction. It's a very explicit construction, but in order to even construct one neighbor, it takes you time polynomial and the size of the graph. The graph itself is of size d power 4t, and you are taking time 2 power t. So it's polynomial in the size of the graph. It's not polylogarithmic in the size of the graph. So we'll do a slightly alternate construction in which construction 2. We haven't yet used just tensor product in this. The h is this once again g1 is the same h square. Gt plus 1 is going to be gt by 2 tensor gt by 2 whole square zigzag with h. So we will take gt by 2, tensor it with gt by 2. And so we are only constructing t's for powers of 2 in this. Is that true? No. Just leave it this way. Yeah. That's the second construction. The claim here I'm going to make if GT is what's the size of this graph? GT I want to claim is a d power 8T. T. T.
Is there going to be another line? Is it that if T is even, then this is GT plus 1, and if T is odd, then are we doing something like that?
Actually, just let's do 2T.
T.
Just T. Just T. That's what it should happen. Yeah. So we are constructing, let's assume we are only constructing for powers of 2. So this is not GT, then this should be G. Yeah, fair enough. I want to claim. Yes. No, H I'm going to initiate H to be something else. H will be now. H is going to be a D power 8 D 1/8 expander. Let's just check why we can do this zigzag product. To do this zigzag product, the degree of this graph should be equal to the size of H. H has D power 8 vertices. So let's ask what's the degree of GT by 2? It's for the degree of DT by 2 is D square. Therefore, when I take tensor product, what is the degrees become? D power 4. And once again, I take a square, the degree become D power 8. So the degrees do match. The degree of this vertex is in fact equal to the side number. So you can, zigzag product is well defined. So in fact, and it should be clear, this is a D power 8T. This is D power 8T minus 1. Each time you're adding a D power 8 to this one. This is actually a D power 8T size graph. Of the degree T square, which is the square of the degree of H. And half, once again, do the induction on the Practical Gap from what we did, the eigenvalue remains half it. So notice eigenvalue started off with 1/8, goes a little higher. Because of the zigzag, it worsens, but because of squaring, it reduces again. Zigzag worsens, squaring reduces. It keeps going back and forth this way. So you keep it under control because of you have zigzag and this one, and similarly, squaring is going to worsen degree. Zigzag improves the degree. So these squaring and this one are doing an alternate this one. Tensoring is letting you go to larger graphs at a much faster rate. Now let's compute what is time t. Time t here is what? So you have to do t by 2. How do you take a step in this?
T by 2.
You take time t by 2, another time t by 2 for both of them, and then a square of them. So it's a 4t time t by 2. So a step in GT will involve, first is you have to take a step, you have to take a step in the graph GT by 2 tensor GT by 2 square. So just the square will contribute 1, 2 here. And then GT by 2, each of them is time t by 2, time t by 2. So you have 2 times time t by 2. That's right. Plus an order 1. So this will be this reduction is a negative t. It's going poly t. If you solve this recurrence, it's because it's going, and that's why you're one. So this is a strongly explicit construction. It's a very nice graph product definition, which actually gives you this sort of keys to construct expander graphs. They have, since this is work due to Reingold, Vadan and Vigdason. Since this work, they have been sort of analyzed this construction a little closely to see how close to Ramanujan you can get. And there have been works which show that you can actually modify the zigzag construction slightly so that you can come very close to Ramanujan. You don't construct exact Ramanujan, but almost Ramanujan graphs you can construct using the zigzag construction. You don't take a step, you take not one step, you take multiple steps. Two steps in a slightly better fashion. There's work by Amnon Tashma and his students who do that, which basically gets you that. By the way, so this work actually won the Godel Prize. Huh? No, that's very recent. This is back, this is good 10-15 years ago. Any questions?
Does the replacement product have any advantage?
You can do it. All of this can be done with replacement product.
Analysis of course.
You can get it's constant. It's just a cleaner analysis, but that also takes constant to constant. You could everything that I can do now, I could have done with a replacement product. It's just that it was first done for the so this lemma. Such a lemma was already known for the replacement product, except that it was not used to construct. This part was known for replacement product. They never did. From that, they didn't go ahead and construct this family of expander graphs the way we constructed it here. Because that was not realized as a potential application for it. But whereas zigzag construction was explicitly, this claim was proven. This claim was proven precisely to do that construction. Hence they did it. Okay. Yeah, so this finishes the basic spectral graph. This one. So this also finishes my initial component in the HDX lecture series. We can start the next topic. Let's take a couple of minutes break and then we'll start the next topic.
Here, so the fully explicit construction, right now we are only constructing something like if you want number of vertices to be some power. So this is a very sparse family, right?
It's a very sparse family.
But I'm guessing like you can, for example, instead of setting GT to be GT by 2, T by 2 thing. So if T was even, you can do this, and if it was odd, you can sort of maybe take a tensor of G T by 2, floor T by 2 ceiling.
Yeah, that will also work. That should work. Yeah, that will work. And because it's the same,
The
analysis is the same. It will work. Yeah. In fact, I think that's what they would write in the paper. Yeah. In fact, there's nothing here itself. I can change it. You're just claiming I just do this.
And we can take this one.
No, GT does that. That's it.
GT.
Yeah. For all T greater than
That's for all T.
For all T greater than 1. Let's take a couple of minute break and then I'll introduce the topic for the next, this one, and we'll talk, find out at 3:30. So this is, I'm going to introduce multiplicative weight update method. Actually. How many of you have seen this? Have you guys seen this multiplicative weight update method in any other, which one?
Theoretical machine.
Theoretical machine learning. Yes. Yeah. So this is sort of It's a core. You will see this very often. Of course, if you do machine learning, this is one of the earliest algorithms you will see in machine learning. What we'll see, we'll build it up slowly, but it is the core of several different algorithms. One is, what are this? It's in machine learning. It's, in fact, there's a whole company that was based out of this called AdaBoost. This is the boosting algorithm. Machine learning. If you study machine learning, you would have seen this. If you're doing optimization, combinatorial optimization, that's in fact in general optimization also. You would see this thing while trying to solve. This is one technique that you will see while trying to solve LP and semi-definite program. You would have seen various techniques. When if you solve LP, there's a simplex method you might have seen. Sometimes you would see the ellipsoid method or the interior point method. One other method uses the multiplicative weight update method. So I just want to say this is a procedure which is at the core of several things. It's also there in getting faster rounding algorithms. And if you're doing a complexity course, I don't know if Ram Prasad plans to teach hardness amplification. And complexity is exactly the heart of it is the multiplicative weight update method. This is due to him. It's a very simple thing which is there, appears in multiple. And by the way, it was not even discovered. This is also one other place where it appears. It's game theory. It might also be part of umangs, especially when you're trying to study zero-sum games and you want to understand its value. And in fact, for several times, this algorithm was discovered and rediscovered within the theoretical computer science literature, not realizing it was the same algorithm. That it was discovered independently by different groups of people. It's a very, very powerful technique that will happen. So what we will see in the next 4 or 5 lectures. Yeah.
What exactly is a rounding algorithm?
So, what's exactly a rounding algorithm? So there are many combinatorial optimization problems for which the exact integer version of the problem is hard. For vertex cover or independent set. Usually
it's an approximation.
It's like an approximation. Yeah. You relax it, you get an LP algorithm, a linear programming thing, which will only give you fractional solutions, and then you want to round the fractional to integral. And it's used in that context. And it's used in that context. So it's used in that context in a very strong sense. That is, you would see this. I'm not sure if it was taught in the first algorithm course. You would see such rounding algorithms. You run an LP and round it to get an approximate solution. There's an original integral solution. You're searching for an integral optimum. The integral optimum is NP hard to obtain. Therefore, you relax the problem. You let the variables not just be 0, 1 variables. You let it be fractional variables between 0 and 1. Now everything can be written as a linear constraint. And you apply some linear LP solver to it, you can solve it. But at the end of it, you get the answers are fractional solutions. They are not integral solutions. You want integral. The independent set, you want to know whether the vertex is in the set or not the set. You don't want to say the probability half, it's in the independent set half. So you need to know how to round it. So there are some ways to do the rounding. Now what we will see is so these algorithms have 2 steps. One is run the LP and then do the rounding. Multiplicative weight update method, we will see this in possibly the 4th lecture in the series. You can skip both these steps. You can do them alternate. Instead of doing the LP solver plus the rounding, you can just run a multiplicative weight update method to replace both of this. And that will be actually much faster than this. It will have the same performance as the LP plus rounding, but running time will be significantly faster than that. So we will in fact get faster rounding algorithms. It will do the LP plus rounding in a much faster sense than the usual way you do that. Running an LP is always a very expensive operation because LPs, you have to run a simplex algorithm or an interior point algorithm, expensive. You always want to avoid running an LP, and this is one way in which we will avoid running an LP. Okay. And our main reference for this course, for this part, on most of my lectures, is going to be an excellent survey article by Aurora, Hazan, and Kale. I'll post this on the site. Most of what I teach in this series of lectures is going to be from this setting. Okay, given a big sort of this one intro for it without telling what this procedure is. So let's spend some time trying to understand what is it. So I'll actually do a warm up to the whole thing first. So the whole setup is the following. You want to invest in a stock or something. You ask n different experts what each one of them tells, and essentially based on their advice, you are going to take this. Or you want to decide which route to travel. You have to travel every day from point A to point B. You turn on 3 different TV channels. Each one tells you traffic is going to be large in these times. The roads, based on that, you pick one of the roads and you go. So each particular day, so that let's assume the setting is going to be there are n experts. These experts might not be right. They call themselves experts, like the TV. This one, they are not necessarily expert, or even the stock predictors. These are all people who tell you how to do it. It's not clear what they are, whether they're experts or not. They call themselves experts. And you listen to all of them. Based on that, you make a decision. So the setting is this. In the morning of each day, you hear the experts giving their advice. Based on their advice, you make a decision. End of the day, you know whether that was the right decision or not. So you can rate every expert, whether what they gave, because you know whether that was the right thing to do or not. Next morning, you once again go back, ask all the experts for their opinion, do it. Now, question is, how do you change your behavior every day based on what you think, how well the experts have performed in the past? So certainly, if some expert is constantly not giving the right answer, you want to not follow that expert in the spot. So you have an expert, you want to change your behavior. You're not going to follow you're going to take an action based on the advice of the experts. There could be contradictory advice to the experts, but you're going to change the way you act as time progresses based on how the experts have performed so far. That's going to be the most general setup. Let's take a very simple case. So let's start. So it's always the case that there are n experts and they give you some advice. And let's for now assume that to build the basic thing, let's assume there is one infallible expert. So the warm-up case is going to be, there is one of the experts who's perfect. He never makes mistakes. But you do not know which of the experts is this. And let's further assume the predictions are all binary. For now, we will later on say the predictions will be some real, it will be this one. Its predictions is just say buy the stock or sell the stock. It's just binary. So that's the warm-up case. I'm going predict. The predictions are binary. 0, 1. More particularly, let 0 stand for, let 1 represent the loss. 1 represent the prediction is gone. Each guy says to take it or not. And at the end of it, so each guy gives an action, tells you a particular way to do. It says to take action A, take action B. There are 2 possible actions. This one, they tell you action A or action B. At the end of the day, and based on it, you make an action, either A or B. And then at the end of the day, you get to see who of them have predicted the right action, who of them are predicted. So you can attribute a 0, 1 vector to what each one of them have said, whether it's right or wrong. So 1 is for loss and 0 is for win. And our goal is to minimize the number of losses. And this happens on time. So once there's a first day, second day, third day, it's going to keep on happening time. You want to eventually minimize the loss. In this case, and suppose one expert was perfect. So how would you go about doing? You follow the setup again. So every day, each expert gives you one of two advices, either A or B. There's one expert who's so based on those experts' advice, you take an action A or B. Now, at the end of the day, you get to know which of the actions was correct. So there is a loss function for you. A or B could have been good for that particular day. There's a loss function for you. There's a loss function for each of the experts. So at the end of the day, you not only know your loss function, you also, because you know what is the right value, which of A or B was the right thing to do. You have this, you can attribute a 0-1 value to your thing, a win-loss for yourself. You can also attribute a 0-1 value for all the experts. Then based on it, next day, you once again, they give you a next bunch of advice, you act on it, and this keep on going. So what would you do? What would be the most? So how would you start this procedure, and how would you keep? But you know that there's one expert out in that bunch who's going to answer correctly all the time. He makes no wrong. He never gives you a wrong advice. So how will you act according to it?
I'll just choose randomly from other.
Okay.
But let's say after K days,
Mm-hmm.
I'll take a look at those advisors whose loss is 0,
Mm-hmm.
and then I'll choose randomly from only those advisors.
Okay. So it's more or less what I'm going to do. Let's make it. I don't want to analyze randomized algorithms right away. We'll do it actually. We'll do that every next lecture. Let's make it even simpler. Let's suppose I only allow the return state. What would you then do? You can modify whatever you said very easily to return a state. How should we modify it?
Just you select one of them.
Oh, you just take all the experts, find out what's the majority of them, which direction are they. That's almost similar to what you said. Pick them, find out which is the most popular view advice given by them. Act accordingly. Now, some of them give the correct advice, some of them give the wrong advice. What would you do? How do you change? You implement your this one?
Yeah, like if I'm wrong, then my the advisor can be wrong. They fall by half everything, right?
So what you do is each time an expert gets it wrong, throw him off the list. So you shrink if another expert gets it wrong, you do the next round, you don't count that expert among the majority again. Keep on shrinking this one. So notice what happens here. Each time you do a mistake, more than half the experts are wrong. That's why, because you actually acted on this one. So each time you make a mistake, you shrink the number of experts by half. So if you ever say, suppose the original number of experts was n. Once you have made more than log n experts, log n mistakes, you have gone down to the single expert. So after log n steps, after not log n days, after you either make less than log n mistakes, or if you have made log n losses, after that you know you're going to be perfectly correct. This is setup clear. So let's formalize this. So let's write the algorithm. So we initialize E to be the set of all experts, E1, E2, En. And this is the set of experts. So E is the set of experts who haven't heard so far. Initial step. Now for each time step, that is for T going from 1 to capital T. Capital T will be the number of days or the number of steps. Act according to the majority. Act according to the majority of the expert's opinion. Then, but experts of majority of the experts' opinion in E, not all the experts, just the current set E. And then you then of course observe the outcome. Eliminate from E all experts third. Okay. Yeah, so this is a very natural algorithm. And that's what we want to do. And what were the two observations we made here? One, the infallible expert always is in E for all T time. He will never go, we will never eliminate him because he's always correct. Two, whenever algorithm errs, the number of experts, the size of E shrinks by half. So this should immediately tell you. Immediate conclusion is number of error of the algorithm. I don't care how well the experts are doing on any such thing. I only care about this algorithm, which is one is always less than or equal to log 2. Yeah. So once if there's an infallible expert, this is the only thing you should. Infallible experts with binary answers. I'm assuming both of those in this setting. This is the only thing to do. Okay. Now let's go on to the slightly general case. We'll state the algorithm, but we'll analyze it next time. But that still won't be the multiplicative weight. We'll change it even more later. But general case in B, the experts are fallible. That there might not be any expert who is good in this. How would you know? Well, so now we have to be careful. What am I trying to do? So let's put up some notation. Let's still work with So I've changed. So I had made two assumptions to begin with. There's an infallible experts and there's only Boolean. The predictions are Boolean. There's only one of two values. Let's still keep the Boolean thing. We'll change that also. Eventually, by the time we discuss the full-fledged multiplicative weight update, we'll change that also. But right now, let's assume still predictions are Boolean. Assume are Boolean binary. That is, there is a 0, 1 set. Now let's set up some notation for each T in T, for each T between such a 1 less than or equal to T less capital T, and each I which is an expert. Small m. Let M use T as a subscript or MTI be 0 if ith expert wins and one otherwise. So this is basically the loss of the ith expert. Let's call it as not wins, errors. And there's also empty, which is similarly, it's the indicator random variable, indicator not random, indicator variable for the algorithm erring at the teeth step. We haven't yet defined what the algorithm is. Whichever algorithm I'm going to talk about that. And what is our goal? Our goal, as before, is always minimize summation empty t going from 1 to t. I want to minimize the algorithm's performance. Question is now, previously we could say that in the infallible case, we could say this number will never cross log n. Now here, it's unclear what does minimize this. What is the, I don't even know what's the right answer that it is varying. So we need to compare it against something. And I say, I will not do worse than a particular thing. So what should we compare it against? So this is our goal. I want to say the number of errors is small and I want to compare it against something. The previous one, I could say it's log n because I knew there was an infallible expert. I could say it's log n. Here, there are two notions. One notion of comparison is for every time step t equals 1 to this one, you find out if there's an expert who gets it right. So this is, you're summing up the best losses. For each step, you're finding out the best expert, how he does, and then taking the summation across t. It could be a different expert for each time t. This minimum is over high. The other is each expert you ask, this is the error that the ith expert makes across the time steps, and you ask what is the error this particular ith expert makes. Which of the two is smaller? One is smaller, one is smaller. One seems a bit unreasonable because each time it could be that there's one guy who's get it correct and it could keep changing. I have no other further information. So what we will try to do, at least initially, we try to guarantee that what the number of errors the algorithm makes is not too far away from, in hindsight, the best expert among the experts whom I'm following. So what we'll do is, this seems a bit unreasonable. In fact, you can show it's infeasible to compare against this. You can come up with examples. You can show that the algorithm, no matter which algorithm performance you give me, I can give you an initial setting in which the difference between that guy and the algorithm's performance and this method will be omega t. Basically, you will be making t errors if you this one. But this one seems a slightly more reasonable thing to do. So for example, if this is like, if there was the infallible expert, you want, this will be the infallible expert over. The infallible expert would have captured it. But now you're assuming there is no infallible expert. So at least in hindsight, there is one expert who's possibly done very well. Initially, he or she might not have done well, but they possibly change as time goes on. But over hindsight, after you look at all the t steps, you know one expert has done the best. You want to rate your performance against this particular expert. So will not go over the algorithm, but what should be the algorithm?
It would be similar to the previous algorithm. Instead of like taking log 0, we take all the advantage with the minimum till then. And to the majority from there.
But what do you do? Previously, you could throw away an expert once you got it wrong because you knew there was an infallible expert. You're sure you're not throwing away the correct expert. Now it might be you cannot throw if you're going to compare yourself against this expert, you can't throw away any expert at any time, because initially this expert might have actually made a lot of bad advice, and later on they actually begin giving good advice.
I don't throw away anything, but every timestamp I take the list of all the experts who have had the best performance till then, and then I choose a majority from them.
No. What do you mean by that?
So let's say at time t equals to 3.
Yeah. Okay, let's do it. And the first step, what you do, you're just going to choose majority. Now the next step, what should we do?
So all the advisors who got it correct in the first step, I take a majority from them.
Yes.
And then at the next step, I calculate performance of all the advisors in the first 2 steps. And then the people who did best, like
Best is what? There could be a person who got it. There could be a person who got good
the total score till then.
total score till then. Okay. For a given slight total score, I don't know how to exactly analyze that one, because so what I will do is will be more similar to the previous one. Called a weighted majority. We'll give everybody weight 1, 1, 1. You observe the observer step. If somebody makes an error, we reduce their weight by half. The others will be basically we are going to reduce their weight of a person by a factor half, or say 1/3 or whatever. We'll reduce it by that factor, but they'll still be included. And which is going to essentially do what you say. There is you penalize a person, an expert, each time they make an error. But now you take majority not based on this one, you take a weighted majority. So you associate a weight with each one. Initially, you associate a weight of 1, 1, 1, 1, 1 to all the experts. And then each time you run those experts, once your outcome comes, you reweight it based on who is erring and who is not erring. So let's write the algorithm, but let's analyze this one. This is called the weighted majority algorithm. WM. For this initialize step. For each expert I from 1 to n, we initialize W, which is WI1 to be equal to 1. And then the algorithm is for t going from 1 to t, A act according to the weighted majority. Is that clear what it means? You just take the weighted majority of this. Basically, you act according to, I can write it formally what it means, but it's a Boolean function. So find how many of them say 0. What are some of the guys who say 0? Some of the guys who say 1. Find which has a larger weight and act according to it. B is observe outcomes. And then we are now going to estimate weights. For all the experts I in N, W T plus 1 for the next round, which is T. The next round T plus 1 of I is WIT itself if I didn't err. And if we erred, it is WIT by 2. I errs. And we continue the process.
If you want these to be the weights directly, then we should also keep normalizing them.
What?
We should
It doesn't matter whether you normalize or not, no? Because you could normalize things, but doesn't change anything, no? Because you're only acting on relative who's doing more or this one. So it doesn't really matter. Everything is just scaling. So it doesn't matter whether you know.
Yeah, then we have to take care of in the how we are calculating the weighted majority.
Yeah. So weighted majority is take all of them who predict 0, find their weights. All of them who predicting 1, find their weights. Whichever is more, act according to it.
The experts who are being wrong more often, they get dampened by the
Yeah, the experts are going to make a lot of errors, their weights are going to constantly reduce. If they make, for instance, if the particular expert makes k errors k times, their weight is going to go less than 1 or 2 to the k. So their contribution to the weighted majority is going to decrease considerably. So what we will do next time is analyze this particular algorithm and ask, and we'll compare these two. We'll compare this guy against this. That will be the weighted majority. Then furthermore, after weighted majority, it will give you we'll almost be able to, but for a log n factor, actually a log t factor, we'll be able to show that this guy, you can make it smaller than twice this guy. It will be no more than twice. Then we'll ask, can you remove the 2? Can you actually make it like 1 plus epsilon for every epsilon of my choice? That's where we'll show that if you introduce randomness into the system, instead of acting according to weighted majority, but if you toss the coin and you have weights and you toss a coin based on this and decide based on that, then actually you can get 1 plus eta. And there we'll observe that once you make that will be what's called the multiplicate weight update method. There we'll analyze that it works not just for Boolean predicates, it works for predicates which are multi-value predicates and all of this. That's what. So the next lecture, we'll analyze both these variants. First, we'll analyze this one. Then we'll extend it to the randomized case. We'll analyze both of them. And then we'll see a whole bunch of applications of this for the next few lectures. Okay, let's stop.